In this example, I need to verify the identity when I have the quantity tangent squared x plus 1 times the quantity tangent squared x minus 1 equals secant raised to the fourth power of x minus 2 times secant squared x. Well, in working with identities, we always want to start working on the more complicated of the two sides. Well, which side is that in this example? They both look equally complicated, so I'm going to start working on the left-hand side. So here's my left-hand side, and there are quite a few different ways to do this problem. I'm going to need to use some identities, and here are some identities that might help. The tangent of x equals sine x over cosine x, and the secant of x is 1 divided by the cosine of x. So I could use these to write everything in terms of sines and cosines, and that method would work, but I think it's the longest method of verifying this identity. Hopefully, when you see an identity that has tangent squared x in and secant squared x, you immediately think of the Pythagorean identity that joins those two. And what is that? It's tangent squared x plus 1 equals secant squared x. I think using this identity will be a lot quicker than writing everything in terms of sines and cosines. So what I'm going to do is instead of this tangent squared x plus 1, I'm going to replace it with secant squared x. So I'm going to have secant squared x multiplied by, now I'm going to have to replace tangent squared x. Well, what is tangent squared x equal? If I subtract 1 from both sides, I get tangent squared x equals secant squared x minus 1. So I'm going to replace this tangent squared x with secant squared x minus 1. And then don't forget, I need the minus 1 that was already in this parentheses. So another minus 1. Now all I have to do is simplify. I have secant squared x times secant squared x. Negative 1 added to negative 1 is minus 2. Now looking at what I have and what I'm trying to prove, am I nearly done? Yes, the only thing left is I need to distribute the secant squared x into this parentheses. So I'm going to get secant squared x times secant squared x, which is the secant of x all raised to the fourth power, which we write as secant to the fourth x. Then I have secant squared x times negative 2 is negative 2 times secant squared x. Is this what I'm trying to prove? Yes, so this equals the right-hand side. So I have shown that the left-hand side equals the right-hand side, so I have verified this identity. One thing I want to stress is this is not the only way to verify this identity. I'm going to briefly describe 2 other methods for completing this problem. Please pause the video if you need extra time to see all the details. So in the next method, I multiplied out my 2 binomials on the left-hand side. This gave me a tan x all raised to the fourth power that I wrote as tan squared x all squared. Then, instead of tan squared x, I wrote secant squared x minus 1. Then I had to multiply this out, collect up like terms, and finally I got the right-hand side. So this second method is a little bit longer than the first method. And finally, looking at the last method I'm going to show you, this is where I write the tangent of x as sine x divided by cosine x, here and here. Now in each parenthesis, I'm going to require a common denominator. Once I've put everything over a common denominator, sine squared x plus cosine squared x, remember, equals 1. So this becomes 1. In the second parenthesis, sine squared x can be written as 1 minus cosine squared x. And then, after a whole lot of simplification, I finally get the right-hand side. So this method is a lot longer than the first two methods, but it does work. So which method should you use? If you can figure out a shorter method, that is great. But as long as you verify the identity, it doesn't matter if your method is shorter or longer than somebody else's, as long as it is correct.